Development Program. I hope that all previous sessions by our experienced expertise prove to be knowledge worthy for all of you present here. Today, I am privileged to welcome our next dignitary, Dr. Rupen Goswami. Sir is currently Associate Professor of Civil Engineering in IIT Madras. Sir has completed his bachelor's in Civil Engineering from Jadavpur University in 1999. Sir has done his Masters of Technology from IIT Kanpur in 2002. Sir has done his PhD from IIT Kanpur in 2007. After that, Sir had joined as an assistant professor at IIT Madras. Sir has a vast experience in teaching field. Sir has also performed eminent work in research areas. Sir has done research in various important fields like earthquake resistant design, design of steel and RC structure, and non-linear response of structures. Sir has 24 publications and 15 journals under his name. Sir's area of interest include earthquake resistant design of RCC, steel and masonry construction. He is working in area of non-linear behavior of structures. Sir has been awarded with ACCE Nagadi Award in 2016 for Best Publication Book in Civil Engineering. He is a member of Core Committee in Bureau of Indian Standards. Now, I would like to invite Dr. Rupen Goswami to share his knowledge and experience with all of us. Over to you, sir.
Thank you very much. You seem to have got all the information from somewhere. Okay. Very good afternoon to all the colleagues out there. I believe other than some students, most of the participants of the faculty development program are colleagues. So warm greetings to all of you. I really do not want to make this as a one-way seminar or a presentation, but rather have the flavor of a classroom kind of a thing. If all these had happened in the pre-corona time, I'm sure we would have had a nice discussion before this session began over a cup of tea or coffee, and then got to know each other better. So just to start the whole process, I would like to know, and maybe you can respond by quickly raising your hand, as to how many of you have taught design courses. It can be concrete design, steel design, doesn't matter. How many of you have taught concrete design courses at either undergraduate or postgraduate levels? Very quickly, just want to see how many of you are in that. Namaskar Bharti ji.
Namaskar, namaskar. आ गए आप?
आ गए. Very. I'm not seeing many of hands. Bharti ji, mic.
माइक तो ऑन ही है.
नहीं उसको ऑफ कर दीजिए. इको आ रहा है.
आप जब शुरू करेंगे तो ऑफ करूंगा ना.
Okay, so I'm seeing only 2 hands raised. That's okay. Now I think hands are coming up. Okay, how many of you have taught earthquake engineering? It can be earthquake engineering, earthquake resistant design, or any such course, not the disaster management course that today we have in most colleges. Okay. Since I am not seeing too many hands, so this you will understand that as a teacher, it helps us understand the class better. So what I'll do is I will definitely do a little bit of a recapitulation of various concepts that I'm sure would have been spoken about since yesterday morning, because today is the second day. So a little bit of a revision always helps in a classroom. So let's do that. I'm going to share my screen, and then at any point in time, if you have any question, please raise your hand, and I'm sure somebody will interrupt me and tell me that there are questions to be answered. I'll be happy to stop and answer your question then and there, rather than keeping everything till the end. Okay, just like a regular classroom kind of an activity. Because once I present, I'll not be able to see the other screen, the Teams screen, so I'll not know if you raise a hand. Okay, so yes. So I've been asked to speak on earthquake behavior of concrete buildings. Of course, there are many aspects, so I'll touch upon the key concepts here once more, and then talk about some of the Indian design provisions that are there, which all of you should be aware of and should be teaching in your classroom. Now, in any class or anything, I always say that one must have all these documents handy in the book form right with you when you are attending any such seminars or classes or anything. Also, you must be having your notebook, pencil, eraser, pen, whatever. And as teacher, I keep doing this, reminding this, because the art of what I find is the art of taking class notes is going, particularly in the Corona period. So let us make it a point that in every class, online, offline, doesn't matter. We will keep reminding everybody that they must be having their class notes and be taking notes. Okay, now the focus of this whole thing is going to be on structural behavior. Although the thing is about design, but essentially it's about structural behavior. And I'm sure you would have come across these terms called force loading versus displacement loading. What's the quick, how do we quickly explain this or understand this? I give you a simple, example of a nice simple cantilever, and I apply a load on top of let's say the midspan, and you will get a deflection there. And if I give the length and give you EI, everything, immediately everybody should be able to quickly get what the delta should be, right? PL cube by 40 ATI. But at the same time, if I give you the same beam and say that I hold the middle portion and pull it down by delta amount and ask what would be the reactions, I'm sure you must be thinking right now in your mind and trying to get the reactions, and it's taking longer than solving the first answer or coming up with the first answer. This is because we are not trained to think in this line. It's the same problem, same question essentially, that we apply a load and the deflection is seen as a consequence of application of that load. The other way of looking at it is, if a displacement is imposed, reactive forces get generated. Why am I talking about this? And this is the fundamental line of thinking that you need to have if you want to discuss earthquake restraint design or earthquake engineering. Now, what is the additional thing in this? That now every material, every structure, every system has a point where it gets damaged. That's usually what we can loosely call as the yield of that system. But provided the structure or the system is capable of deforming beyond that yield point, it is possible to apply more displacement beyond the yield displacement on a structure, provided the system is ductile. The system is not going to fail. It's not going to fail. And I'm making a very important distinction here between damage and failure. Damage is not a bad thing, so in a certain way, but failure is something that we must look out for, keep an eye out for. So as you can see that it is possible for systems to accommodate more displacement beyond its yield displacement, provided the system is ductile. So therefore, what happens in that beam example, if I try to apply a load more than its strength capacity, and if the system is not ductile, it will suddenly fail. However, if the system is ductile enough, it will continue to deform with the with more and more imposed displacement, and it will undergo this post-yield plastic deformation. When that happens, we define a quantity called ductility capacity as the ratio of the ultimate plastic deformation before failure to the yield deformation. And this we all know is an important quantity that we always talk about when we discuss earthquake restraint design. So the fundamental thing is that if you have a ductile system, and which essentially means that if the system has enough ductility capacity, the system can sustain more larger displacements than its yield displacement, or the displacement at which the system is likely to see damage. Why is this important? Because earthquakes do not, and I repeat, do not apply any force or load on the structures, but they just impose this displacement. They shake the base of the building, which is essentially a displacement loading. So what happens is that the bigger the earthquake, the larger is the displacement that is imposed at the base of a structure, and the structure should be designed to sustain that displacement loading. right? And this is the fundamental difference that you have to bring out, that earthquake is not a force, it is a displacement of different magnitudes. Now, what is this level of shaking that we are talking about? Of course, if we go back, we all know the difference between magnitude and intensity. So you have an earthquake there. Near the epicenter, you will have larger shaking for the same earthquake, and the farther away you go, you will have lesser and lesser level of shaking. So we talk about different levels of shaking that can be experienced at a particular site. And this is where we bring in the concepts of, let's say, a minor level of shaking, moderate level of shaking, severe level of shaking, and so on and so forth. How are these defined? There are ways to define these. Let's not get into that, but effectively what we say is that these small levels of shaking at a given place can occur in large number of events, whereas these very large ones occur very rarely. So therefore, we develop a design philosophy where we say that the structures should be able to sustain the big one properly, because the big one, the severe one, is also likely to occur at that particular site for a given structure. So therefore, if we look at the design, what is the design that we need to do? If we say that, okay, at a given site, I need to design a structure, and the structure is going to be shaken by 3 different earthquakes, minor, moderate, severe, which are going to impose larger and larger displacements. Okay, so what is the loading here? It's the displacement loading. And if I say I do not want any damage in the structure, nothing should happen to my structure, then for the biggest event, this is what is generally referred as the maximum considered earthquake. For that level of shaking, we would be able to come up with this maximum level of lateral force, which would be induced in the system as a reaction to that displacement which is going to be imposed. And if we do not want any damage in our system, then obviously we know that this is the force for which we should design our structure to have that much strength capacity. But then often this becomes very uneconomical, so to speak, because we do not know if that rare event, that big event, which is very rare, is ever going to occur during the design life of the structure or not. So this is where we come and say that, look, earthquake is not a force loading, it is a displacement loading. And therefore, and it is not also guaranteed that this biggest event, this maximum considered earthquake, is going to occur during the design life of the structure. So therefore, why don't we design the structure in a different way, such that if that big earthquake happens, let it get damaged. We will provide enough deformability and ductility to the structure so that even after getting damage, it does not fail, it does not collapse, but we know that it will get damaged. So in that case, what will happen is that this is the maximum amount of lateral force that would be induced in the system if we adopt this design strategy. So now if I put both of them together and ask you which structure you would, as a structural engineer, choose to design, I'm sure almost all of you will say we will choose to design the yellow structure and not the green structure. If I ask why, obvious answer will be this will be more economical because we have to design for lesser strength. So the first myth that earthquake resistant design is costlier has to be broken. In the design philosophy, by adopting this strategy itself, we are ensuring that earthquake resistant design is much costlier, much economical compared to a design where if you had adopted the strategy that nothing would happen to my structure, the structure would remain elastic, right? So now this is what we do, and therefore we say that earthquake resistant design, the philosophy is that we accept damage, and this is why I said that damage is not a crime. Having damage is not a crime. But what we need to ensure is that those large number of small little earthquakes, that the minor earthquakes that will keep happening at that site, we do not want our structure to get damaged every day or every week or every month or every year. So those kind of smaller events must be registered without damage. So you can see that the structure up to about this level still is linearly elastic. That means nothing happens. The large number of small earthquakes will still be registered without damage. When the moderate event comes, maybe there will be some damage, but those damage we should be able to repair and retrofit. But the only condition that we impose is that if that big event happens, my structure must not collapse. So this is how we set the whole design philosophy for earthquake resistant design. And this is where this is so special and unique that under no other load combination, if you are asked to design a beam to carry a certain dead load or even a live load, you will not design it to get damaged under the action of the dead load or live load. You will always try to design it to remain proper functional. But here in earthquake resistant design, we deliberately, consciously allow our structure to get damaged if that moderate or the big event happens. But of course, we ensure that under a large number of smaller events that are likely at that site, the structure should remain essentially linearly elastic. That means functional, so to speak. Okay, so this is the fundamental distinction between earthquake resistant design and any other design. And this is possible only and only because earthquake is not a force loading. You cannot apply the same strategy, let's say, for wind loading or any other type of loading for that matter, because those are not displacement loading, those are force loading, right? So this is the fundamental first point that we must teach in classroom. So what happens? We understood this philosophy for last 60, 70 years. People started designing structures. We started developing design codes. Of course, design codes will always evolve. Even today, we are going on improving our design standards and so on. So the rest of the world is also doing. But still, we found that structures did fail, did collapse for various reasons. So if you saw open ground story failure there, here in this particular structure, you see that all the beam column joints have failed. And this is an important concept that we must teach in class, how to design beam column joints. If you think that only concrete buildings have suffered damage and failure, no, steel buildings have also failed, collapsed. In 1985, 21-story steel building, I mean, definitely you would call it a tall building. You can see the fate of that, of such a building here in 1985 Mexico City earthquake. A steel building, tall building, steel also, often there is a misconception that steel is a ductile material, therefore steel structures are ductile. You can see the fate of a steel building. If you thought buildings only have failed, no, bridges have also failed with a much higher level of engineering going into, and you can see the kind of collapse that has happened, not just in steel, again in reinforced concrete. So across the aisle, you are seeing that something we have not been doing correct. What is this something? We didn't understand well enough that earthquake is a displacement loading. We tried applying our same strength or load-based design concepts to earthquake, to resist earthquakes, and this is where we failed. We failed over the years. Okay, this is a picture I wanted to show and deliberately, because you will be able to relate to a lot of structures coming up in many cities today in India, which have this single pier and then something else is going to go above it. Okay, so there is definitely scope for us to learn how to design these structures properly. So we saw that we started off with a philosophy, but then did not really manage to fulfill that dream, and structures collapsed. So now if I show you this picture and ask you, why did these structures collapse? The answer is not because they did not have enough strength capacity, but because they did not have enough displacement capacity or deformability or ductility capacity. Strength has never been a problem. Trust me, all the failures have always been associated with lack of displacement capacity. It is not because of lack of strength that structures have collapsed and fallen during earthquakes ever, anywhere in the world. So this is where this brings us to this point where we must understand that there are various aspects that we need to take care of in earthquake resistant design, starting with configuration, minimum lateral stiffness. Of course, we need to provide some minimum lateral strength, and we'll discuss why in a few minutes. Then deformability, extremely important, because earthquake is only going to demand deformability because it's a displacement loading, right? That is what the earthquake is going to demand. And so deformability is the fundamental quantity here. Then, of course, since we are going to allow damage, so therefore we talk about ductility, and then we need a mechanism, a collapse mechanism, to be able to maximize the last quantity, what is called the energy dissipation capacity. So earthquakes are, during that shaking, a lot of energy is released, and that is why the ground is shaking, and those a part of that energy gets transmitted into the structure during that earthquake shaking, and the structure should be able to dissipate that energy as fast as it can. And one of the key purposes of letting a structure getting damaged is to dissipate that amount of energy faster. Otherwise, the structure, if it were to remain elastic, remember, it would have gone on oscillating back and forth for days after an earthquake is over, right? So we want the structure to come back to rest as fast as possible, and the only way of doing that is to be able to dissipate that energy, and that dissipation happens if we allow good damage to occur in our structures. Okay, I added a new qualifier to damage, which is good damage, and the whole idea is to balance this whole thing about good damage, identify good damage from bad damages, because bad damages are going to cause failure, collapse. Good damages need not. So let's quickly review our current practice. What is it that we do? And this is where I will request you to open your eyes 1893 part 1, which is the basic code. Keep it in front of you so that you can quickly follow up and see what I'm talking about. Two primary quantities that we need to keep in mind when we talk about the force-based earthquake resistant design. The first is ductility. We have already seen what ductility is. Only thing that I'm saying in addition to what I've said until now is that often we overestimate ductility capacity. Okay, we'll see why. The second most important thing to understand here is the concept of overstrength. I'm sure most of you have come across this item called overstrength. Very quickly, what is overstrength? If you are asked to design, let's say you are asked to design a reinforced concrete beam, simple beam, for a design moment of 100 kilonewton meter moment. Let's say a reinforced concrete beam, it can be a steel beam, it doesn't matter. Let's say reinforced concrete beam. You will come up with the cross section, grade of concrete, amount of reinforcement, everything. You come up with a design. Let's say you cast that beam and you take it to the laboratory in your college and test that beam. If you do a test, and if you have done everything right, properly, followed all the design methods, let's say limit state design method as given in IS 456, then what you will find is the beam will actually be able to carry a moment larger than that 100 kilonewton meter for which you started the design, right? So this additional strength is what is essentially the overstrength. Now, when you add all these members, all these beams, columns, slabs, everything, joints, everything put together and create a structure. So structures also have a overstrength. By the end of this, talk, I will request you to maybe type in your answer in the chat. Is overstrength good or bad in the context of earthquake resistant design? Okay, that's an important question. Is overstrength good or bad? Because the obvious thought comes to my mind, is that, okay, if I've designed for 100 and I'm getting more than 100, it must be good. Okay, that's the obvious line of thinking that we tell you. So coming back to this particular aspect, that we see that there is a cat and mouse game going on. So for instance, if I design the structure for a force level here, I will end up getting a structure whose strength capacity will be higher. If I design it there, it will go up higher. So what we do in earthquake resistant design is that even before we start doing the design, we account for this overstrength and actually design it for even a lesser force. So in earthquake resistant design, what we do is that this would have been the force for which we would have designed our structures if we had wanted the structure to remain elastic. We said, no, 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 that's too costly. Let us, make it economic. So we come here and then we realize that if we design here, the capacity would go beyond that. So we actually come down and say, okay, let us design for this level of force so that my structural capacity will be sitting here. We actually consider this aspect even at right at the start of the design. So that is where the concept of use of response reduction factor comes. So we estimate this elastic force. Why elastic? Because we know elastic analysis. Even the dynamic analysis that we do is linear dynamic analysis. So this is what we get, and then we straight away divide that by a response reduction factor. We come to this force level, which is almost like 10% of what the force we should have ideally designed our structure for. So you can see the level of economy that we are talking about here in earthquake resistant design. So it's a two-step process. First, we calculate the maximum elastic seismic forces based on our elastic analysis, linear dynamic analysis, linear static analysis, whatever, and then reduce it by a response reduction factor to account for these two things, which we are at this level, we have not even started the design, but we are accounting for, because through our design, we should be able to provide for these two. So that's a promise for the future in the design process. Now the question is, so depending on, as I was saying, that we can actually choose to do a reduction at multiple levels. Which is the right value to choose? Now, this is where let's understand a very important thing. Forget about overstrength for a time being. So initially, I would have done this, but since it's too costly, I say no, no, no. Please reduce the cost of the design. So you, as a let's say a structural engineer, you can come and say that okay, instead of this, I will give you a structure which is going to have so much of capacity. But the only fact is, remember, the demand is here. Demand is not from the force. It's not a force loading. It is a displacement loading. So this demand is going to remain more or less same. So in that case, what you are going to have is you are going to see this much damage in the system, and therefore you have to provide for so much of ductility capacity. I say, okay, but I don't understand ductility, but the cost is still more. Please reduce the cost of the design. So you say, okay, I give you another option. I can design your structure to have so much capacity, but in this case, your ductility requirement is higher. I say, no, 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 I don't understand ductility. Please reduce cost. You can give a third option, but in this case, you can see the ductility requirement is going to be even higher. So a common man, a client, will not understand this concept of ductility. The only thing he or she, they will understand is how much is the cost, and they will ask you to cut down on the cost. So you have an option to keep reducing the strength capacity of the structure, thereby reducing cost of your design. But the question is, what is the limit? Can you bring this force down to the very, very small level and say that that is the design? The answer is no, because there is a practical limit of how much ductility you can provide in your structure. You cannot cross that limit. And this is where design codes come in and give you the force that you must design your structure for. That is the only purpose of defining a force, so-called earthquake load, that you put in your load combination or create a load case for as EL based on the IS 1893. Because you cannot go on reducing this forever, because the demand for ductility will be so high, it will not be possible to practically provide for it. Right? So it's a trade-off between strength and ductility. It is a trade-off between this, and this is the concept that a student must understand in class. So coming back to code, IS 1893 part 1. So this is what it says, and all this, you know that it gives a spectral shape, something like this. It defines it. We start off with a zone factor. Mind you, I'll repeat once more here that these zone factors, or what we design for as a structure, is we design structures to sustain a certain level of shaking. That is, we design structures for intensity of shaking. We do not design structures for certain magnitudes of earthquakes. Okay, it's a very important concept for you to remember, that we do not design structures for a certain magnitude. If somebody asks a question, have you designed this structure for magnitude 6 or 7? That's a wrong question. It should be, what is the intensity of shaking for which this structure has been designed for? That's the right question to ask. Okay, moving on quickly. So the design spectra are given in the design codes, and now since 2016 we use this same fixed value of damping, which is 5% for all types of structures. We do not distinguish between steel structures and concrete structures and masonry structures. 5% for everything for the purpose of doing design. Why is that? Because remember, the strength is not the important criteria. By changing the damping, you will get different force levels, but that is not the important criteria in governing the safety of the structure. Whether the structure will collapse or not is not governed by the strength. It is governed by the displacement capacity, or the deformability, or the ductility capacity. So it doesn't matter. Then we have response reduction factors. So that is where the R also is kind of same. Earlier steel structures, similar steel structures were asked to be designed for a much higher force, and that was another reason why concrete buildings were more competitive compared to steel buildings. But today Indian standards is trying to maintain this level playing field between both types of structures. So we should be able to design more of steel structures in future. Okay, but then we can do any analysis and all, but there must be a certain minimum design force. Once again, even after doing analysis. So this is where there is another requirement that talks about the minimum horizon. You can do all the analysis, but still this is what we have to design our structures for. Sometimes we also need to, for certain special situations and special types of structures, we need to consider vertical shaking, and that is also given in IS 1893 part 1. Why am I showing you all this? Because you should be able to see all these items in the code and be able to talk about all this. Natural period, and these are all empirical relations, typically for the low-rise or mid-rise structures. Now, of course, the definition of low-rise, mid-rise, or tall, high-rise buildings is ever-changing, right? What was tall 70 years back or 100 years back is a low-rise structure today, right? So I'll not go into the definition of those, but these are generally valid for low-rise structures or mid-rise structures, and not for tall buildings as such. Then in doing that analysis, we talk about crack section properties. You have to consider this, because we know that reinforced concrete, for the kind of design that we use, limit state design, for example, we assume crack section properties. So concrete is going to be cracked, so therefore it's more, and particularly remember, since we are talking earthquake resistant design, the cracking is only going to be more because we are going to allow damage to happen. So therefore there is a need to use crack section properties, and these values are also given for two types of analysis, serviceability and strength. I'm showing here for what is to be used for strength design. Finally, now we said that we are going to allow damage. It is possible because earthquake is a displacement loading. So long we provide the ductility capacity, we should be able to allow damage. Very good. But with damage comes a challenge, because certain types of structures, we do not want damage to happen, right? So there are various types of structures which are classified where we want to minimize that damage, and the only way now to do that is to actually design these structures for higher force levels, and that we bring in through the importance factor, essentially, so that we know that these structures are designed for little higher force levels, and therefore the damage, the ductility demand is going to be less. So we kind of use that strategy, and that is how you see this, okay, as the design based shear that we then kind of distribute along the height of the structure into different lateral load resisting elements and design or analyze our structures and start the design process. So we do all this, and in this whole activity, this response reduction factor becomes once again the important aspect. We said it is composed of two parts, ductility and overstrength. There is another third part which is subsumed into the overstrength aspect, is what is called the redundancy. So what you see here is, this is important to understand, that if you design a structure for this force level, the first damage, let's say the first yield, is going to happen at a force level higher than that. And then it is going to reach a capacity beyond this, and that usually happens because of redundancy. Now, the survivability of the structure, that means whether the structure will collapse or not, doesn't depend on any of these. All it depends on is this deformability. If this deformability is not going to be there, no matter what you put as these strength levels, the structure is going to collapse, right? And the important part to understand here is that in the current practice of design that we are doing, we do not check at the end of the design process whether this displacement capacity or the ductility capacity has been provided or not. We do not have a check for that. And that is the most dangerous thing that is currently happening. Now, so why did the design codes did not put that check till now? For various reasons. But before going into that, let us understand one thing. That design code is not just about providing you that strength value. It is about so many other things also. And by doing certain other things, it is expected that a certain amount, minimum amount of deformability and ductility capacity will be provided you follow in both letter and spirit all the other requirements of the standards. Okay, all the other requirements of the standards. So that is how this whole concept is built on. Because otherwise one needs to do a nonlinear analysis, which is not kind of a very commonly taught in engineering colleges, even today across the country. So the next question is that, so therefore, without getting into those details, how do we actually provide this deformability and ductility? So let me pose a simple question. This is the question that I usually pose in the class, which is, how do you build a ductile structure? Now, we saw right at the beginning that there are two types of behavior. One is brittle, the other is ductile. If we want ductile structures, we must prevent all the brittle modes of failures happening in a structure, right? So that's the fundamental thing. So therefore, the next logical thing to discuss in a class is, so therefore, what are the different ductile modes of damage and brittle modes of failure possible in a, let's say, a reinforced concrete structure? So if you should be able to create a list in a class through discussion in the class. Let the students come up with all these answers. They may take a while, but here's a list that for reinforced concrete, only under reinforced flexural behavior is a ductile mode. Everything else is brittle. Over reinforced, of course, is a brittle action. Shear failure is a brittle action. Axial action is a brittle. Anchorage bond brittle. Buckling of rebars with when you do not provide adequate transverse reinforcement. These are all brittle modes of failures. So if you want a reinforced concrete structure to be, or let's say a building to be ductile, you must ensure that all these brittle modes of failure do not come into the picture. Question is how? That is what we'll see. Similarly, you can create a list for steel structures. I'm sure somebody else will be talking about all these items when you discuss earthquake resistant design of steel buildings. The next question is, okay, so we are going to allow damage to happen. Those damages must be ductile in nature, very good. But where? Where in the structure can we allow those damages to happen? Of course, the first answer is we cannot, it is absolutely not acceptable to have damage in the soil and in the foundation. It is undesirable to have damage in columns and joints. for reasons we'll see very quickly. So the only place that where we can allow this damage to happen, a ductile damage, is at the ends of the beams and in structural walls. When I'm saying structural walls, I'm talking about reinforced concrete walls because we are discussing reinforced concrete buildings. So these are the only locations where we can allow this to happen. So we have identified that. So we'll allow damage, yes, of what type? Ductile type, where? At favorable locations, which are the ends of the beams in frame buildings. How do we now provide? Okay, we know where to provide the what type of damage. How do we therefore now provide ductility? Now, in reinforced concrete buildings, particularly in modern day, very important thing is happening is the use of higher strength materials, which is flooding the market very fast, or rather it has already actually captured the market. Okay, so ductility we need to provide at the material level, section level, member level, and structure level. For a team to be a world champion team, you need, let's say, a football team, you need a good goalkeeper, you need a very strong defense, you need a strong midfield, and a good, forward lineup. So you need the structure. For the structure to be ductile, you need its members to be ductile, you need its cross sections. That means you need under reinforced cross section as against over reinforced cross sections, and you need good materials. The question is, high strength concrete is good or bad for this ductility aspect? The thing is that people often think that by providing high strength steel, you can make structures more earthquake resistant. That is absolutely wrong, because what you see is that high strength concrete has lesser deformation capacity, less strain capacity. They cannot deform, they cannot strain more. So it's a myth that by going for high strength concrete, we can make earthquake resistant structures. And in the market, sometimes I see blatant lies like this, where you will see advertisements of reinforcing steel claiming the steel to be earthquake resistant. Trust me, as structural engineer, nothing can make your structure ductile except your design. So don't fall for all these items. All you have is concrete, steel, you have to make them work together. And one of the key aspects is to provide adequate transverse reinforcement and provide ductility for confinement to your concrete. That's the only way you can make your structure ductile. Don't fall for all those items. To prove my point, I'll quickly show a simple example. So what you see on the left hand side and on the right hand side are two simple frame buildings. And by the look of them, you must be able to identify that here, what you see is that the columns are very small, nice, slender looking columns, but the beams are, as usual, deeper. And in the other case, you have these columns relatively bigger and stronger and stiffer compared to the beams. So I'm just showing a numerical example of a benchmark building. There are a couple of aspects about detailing that here, of course, we are also, in addition to that, we are providing nice closely spaced stirrups with 135-degree hooks, whereas in the other one, we are not providing the 135-degree hook, and also the spacing is more and so on and so forth. Column sizes are also different. What it does is this kind of a 135-degree hook does not allow confinement of concrete because they open up very quickly, and obviously your concrete doesn't get confined. So as a result, what happens is these columns that you see is they're all going to be extremely brittle in nature. Okay, because you're not providing the confinement, so to speak. The second aspect in column design is one must get into PM interaction curve, and we only look at the curve and see whether the particular design point is safe or unsafe. But at the same time, we must look at the moment curvature or moment rotation relationship. There is something called a balance point, and if you go over the balance point, even if you have confined it properly, you will see that the column section will have very little ductility. These are almost like brittle actions. So when you have smaller size columns, the axial stress ratio is going to be very high, classically, typically much above the balance point. And even in those, even if you provide all the transverse reinforcement with 135-degree hook, those are not going to be utilized. They're going to be waste because your column section is still not going to be ductile enough. It is only when you stay below the balance point that you can see adequate ductility coming into the picture, and this is where your transverse reinforcement with 135-degree hook will actually work. Okay, so it's very important that we discuss the importance of balance point in a classroom and emphasize that how columns should be designed. So small columns, if we start off with small columns, the axial stress ratio will be very high, and then if we do not do the detailing also, of course we'll have brittle failure, where in contrast to larger size columns with that. So this is just an analysis, a pushover analysis result. So you can see immediately hinges form in the column, and then the structure will collapse as quickly as that. However, if I do a proper design of columns, I can see that now I'm able to push damages of ductile nature, flexural actions happening at the beam ends, and you can see the structure is able to laterally deform without collapsing. That means what? The structure is now provided with that required lateral deformability or displacement capacity to sustain or resist the displacement that a large earthquake is going to impose on the structure. Remember, once again, I'll say the demand is not any force being applied on the structure, but the displacement imposed at the base of the structure. So you can see this nice formation of plastic hinges, as we call them, and yet the structure is able to move forward. So now if I show you the total lateral load base shear versus roof displacement curve, you will see one stops abruptly here because it's going to fail thereafter, whereas the other one goes, has much higher lateral displacement capacity, and you can see a ductile behavior coming out of this. This is why we talk about designing columns properly, and from this concept of having stronger, stiffer columns come into the picture. So the column who's supporting the beam must be stronger than the beam, right? So that is the whole concept of weak column, strong beam versus strong column, weak beam. Of course, here at this stage, I have not considered the behavior of the joint. Remember, we saw a picture where the beam column joint failed. We can design the column properly, we can design the beam properly, but if we do not design the joint, which is sitting between these two components, of course, the damage will happen in the joint. So here the discussion is about between the beam and the column. So if we do not follow strong column, weak beam, we see that at very small lateral displacement, the structure collapses. An earthquake is, let's say, imposing so much of demand, so obviously these structures will not sustain, they will collapse. And that is where, now if you take it to a reverse cyclic loading kind of a response, because earthquake is back and forth motion, then you see that the area under this lateral force, lateral displacement curve in this case is much larger, which essentially means structures designed to have designed with strong column weak beam philosophy will have much larger energy dissipation capacity compared to weak column strong beam design. Okay, so that is another reason why we must adopt strong column weak beam design. When we say columns have to be stronger than the beam, we are talking about a relative strength ratio. How do we arrive at that? How do we fix, by how much should the column be stronger than the beam, and so on and so forth? To understand this, we must understand the concept of capacity design. What is capacity design? Very quickly, I'll try to explain this. There are two aspects to it. The first is a hierarchy of strength. So when I say column stronger than the beam, I'm talking about a hierarchy of strength. And what does it lead to? It leads to a sequencing of damage, because the component which has relatively lesser strength is going to see the damage first. We'll see this as an example. I'm sure you must have come across this chain analogy, a very classic thing. What we say is that the strength and ductility of the chain depends on the strength and ductility of its weakest link. So let's say we are trying to make a chain out of out of these different links, where we use two types of links. One, the blue one, and the other is the red one. Now we have two options. I give you two options. Okay. In one case, I use strong brittle links, let's say a large number of those, and only one weak ductile link. What is weak? You can see the strength capacity of this is lesser than this. So relative to the brittle links, this one is weaker. In the second option, I create again a chain with large number of brittle links whose strength capacity is lesser than one ductile link, but which is stronger. I want to understand which is the correct option A or option B for me to choose. Okay, this is where can I do a quick, I know this is monotonous, so I want to go back and see the screen. Those of you who believe that option A is the correct answer, please raise your hand. I want to see how many of you raise your hand for option A. I see 2 hands. Okay. Okay. How many of you think option B is the right answer? Please raise your hand. Okay. Okay. But I see a lot more participants than the total number of hands. So this is what happened in electronic voting. Yes, no, and then don't know and won't tell you what I'm thinking is the last option. Others, please join in either this way or that way. You have to take a stand. Okay. Let's see what the right answer is. So what happens here is, if you go back to the chain, if you see the force is same in all the chains, and therefore the first option gives you a ductile chain, the second option gives you a brittle chain. Why? Because the strength of the chain depends on the strength of the weakest link. Weak is whichever has the least one. So damage happens here or damage happens here. And once damage happens, what type of damage is what comes into the picture? In this case, it is going to be a ductile damage, and so the behavior of the chain is going to be ductile, whereas here the damage is going to be of a brittle type, and therefore you will see a brittle failure of the chain itself. So what do we learn here? There are 2 things to learn. That the ductile, if you want the structure to be ductile, remember I said we have to eliminate possibility of all the brittle failures to happen. How do you eliminate that? By having a hierarchy of strength, by ensuring that the brittle actions have a strength higher than that of the ductile action. Right? The ductile one has to be the weakest one. Then you will get a ductile behavior. If you make the brittle actions weaker than this ductile action, then you will have brittle failure. So that's the first aspect. So let's look at it. So step 1, very important, is to understand the overstrength capacity of the ductile component, the ductile link in this example. If we underestimate the overstrength of the ductile link, we will not be able to set a benchmark for the design of the brittle link. Okay, please note this down. Think about this very, this is very important. So we must be able to estimate properly the overstrength capacity of the ductile link. Then and only then we will be able to design the brittle link to have a design strength higher than the overstrength of the weak ductile link. Okay, that is the design strategy. How do we use this in real structural engineering? Let's come back to this frame building. So we have beams and columns. So I'm not bringing into discussion the beam column joint. So between the beam and the column, which one should be stronger? We know the column is supporting the beam, therefore columns have to be stronger. So, and we also saw in most cases columns do not give that ductile behavior, but beams we know we can make them adequately under reinforced and they will be ductile. So the weakest link here has to be the beam, and therefore we must estimate the overstrength capacity, not the design capacity. So how do we go about doing that? We have the load already calculated, the code-based forces. You have done your linear elastic analysis. You have got your bending moment shear force in all the members through the factored load combinations. Everything is done. You know the bending moment and the shear force of the beam. Design the beam. Design them to be under reinforced. You have got your reinforcements and everything. Now at this stage, let's go back to that example that let's say to design this beam, the design moment, factored moment was 100 kilonewton meter. You come up with all the reinforcements and now you will estimate what could be the possible overstrength of this beam. Overstrength happens due to various reasons. One of them is that at the design stage, you used a partial safety factor of 0.87, that means you kept the stress level below the yield. So real structure, when actual earthquake comes on the structure, it will not know that you have used a partial safety factor of 0.87 or something like that. So it will behave on its own. So we must remove that safety factor. Also, we usually design keeping Fy in mind, but actually the steel can go into strain hardening. So we kind of, based on a lot of experimental data and experience, we have understood that about 20% excess strength is possible. So together these two gives you this factor of approximately 1.3 something. So 1.4 times mu. So this is your ultimate capacity as estimated based on IS 456. But your actual maximum probable moment that will be generated in the beam is 40% more. Now you come back and see, based on this moment, what is the maximum shear that might get generated. And that is the equilibrium based shear for which you need to design, because shear is a brittle action. If you do not design the beam for this enhanced shear, then what will happen? The brittle action will have a lesser strength capacity and therefore will get triggered first. So your beam will fail in shear. And that is the whole idea of the capacity design that you see in IS 13920. Okay, so IS 13920, I want to say this loudly and clearly, is not a ductile detailing code. It is a design and detailing code. Detailing alone is not going to make your structure earthquake resistant. You need to do proper design also. There is a lot of misconception. A lot of people very loosely say that I have done ductile detailing, therefore my structure is earthquake resistant. No, absolutely not. It is not guaranteed. Okay, there is a design that is involved even before you get into doing the detailing. Please keep this in focus. Okay, so now we have designed the beam and the column. Remember, we started off by talking about how much should the column be stronger than the beam. So we have got all these values. We have designed the beam. We have designed the beam for shear also. And now if we now look at this portion of the frame and do ensure force equilibrium, then we see that these columns are subjected to shear force. And we calculate that shear force. And now please ensure that columns are designed for shear. This is where I'll request you to open up IS 456 and find for yourself which is that clause that gives you how to design that column, how to design columns for shear. I want you to find out that those clauses from IS 456, and please do this exercise with utmost sincerity. This is important. Okay, because if you do not design your columns for shear, obviously your columns are going to fail, not just fail, but fail in the most brittle manner possible, which is failure in shear. Let's come to beam column joint, because until now we have been keeping this aside, but not anymore. So if you look at the force equilibrium, obviously this joint is subjected to different forces, moments and shear coming on it from different directions. We need to ensure two things, that at a joint we have adequate moment capacity between the columns and these beams. So this is where the strength ratio between the column and beam comes into the picture. Our design codes say that, remember we saw that the beam's maximum overstrength is approximately about 40% more than the ultimate capacity estimated as per IS 456. So therefore the columns must at least be stronger than that value. So that is the logic behind this. But I want you to pay attention to a simulation result here. So this is bending moment diagram that you are seeing here on a frame building when subjected to a certain ground motions. I'll not go into the details of the design and so on and so forth, but what is important is that initially you see this nice triangular bending moment diagram that we are all familiar with. But once damage starts happening, you will see that let's say for instance here, you don't see that reverse curvature in the columns, right? So this aspect that we always assume that these moments are, these columns and the beams are all bending in double curvature is not always true. Under static analysis, we will always find that, but under dynamic conditions, that may not always be honored. And so what we see is that that factor, the strength ratio that we found, has to be enhanced to take into account some of those aspects. So as an example, we enhanced it to a strength ratio of 1.6. You can see that the column still failed under dynamic action. Although static analysis will give you a safe design, but under dynamic action, it still failed. Whereas now we enhanced it to about 2.8, and you will be able to see that yes, now it's able to sustain that particular shape. Is this the final answer? The answer is no. It depends on your entire design. It depends on the size of your structure, how many bays, how many stories, what are the column sizes, what are the beam sizes, and so on and so forth. Right? So all these together will dictate this number. No one single number will be universally applicable. So therefore, the design codes come and give you a bare minimum requirement. So this particular clause in IS 13920 that you see is a bare minimum. This does not guarantee that your structure is going to be resisting the whole thing. In fact, in steel, you'll in IS 800, you will find a similar clause. There, the number is even more challenging. Okay, so a lot more studies need to be done, effectively understanding what should be this margin when you try to set the strength hierarchy between different components and between different actions. So most of the design codes, particularly IS 13920 and IS 800 section 12, most of the design provisions that you have are fundamentally based on this concept of capacity design. So next time when you read all these clauses, keep this in mind, and I'm sure this will help you understand the requirements even better. Very quickly, I'll move on. So we saw that smaller columns, higher axial load ratio, high up on the PM interaction diagram, difficult because no ductility. We need to design columns for shear, otherwise columns will fail in shear. There are other physical, more intuitive aspects also. So one important thing that you must take note of that earlier IS 13920 used to have a diagram like this, that this top reinforcement has to be provided with a development length, which used to go inside. Concrete used to be poured up to here, so nobody used to provide that anchorage to even the beam reinforcement. Right now, so therefore, there is a minimum size of columns that has come, which is 300 and 20 times the largest beam rebar diameter, so that this is a simpler detailing that we can follow. Another very practical aspect is that we have the beam and the column of the same width. And so the only way to take the beam reinforcement through the column is to bend the bars. You take a metal, these pins or gems clip, right? Bend it like that and try to apply tension. You will see you can apply tension on a bent reinforcement bar only when the reinforcement straightens out. So in this case, imagine if this wants to straighten out because of the tension, what it is going to do, it is going to push outwards all the column reinforcement. So you're going to have tremendous amount of cracking in the joint, and therefore you are going to weaken the joint. So the best thing is to have a wider column than the beam. You can see the beam reinforcement is actually going beyond the column reinforcement, because beam cover is 25 mm and column cover is 40 mm. So how can this reinforcement go inside? So this is bad. This is definitely bad. Now, finally, once you have taken care of all the simpler things, what is happening to the joint? So under lateral load, the joint is subjected to a very unique situation where the bars, the reinforcing bars that goes through the joint of the beam, they get pulled or pushed in one direction from both sides. Now, you do a simple calculation about the bond requirement, and you will be surprised to get the result. You please do that exercise. I do not have time to do all that, but to kind of cater to some of these aspects, today we have a requirement that the minimum column width should be greater than 20 times the largest beam rebar diameter. So if you want to keep your column size small, you have to keep your beam reinforcement dia small. And if you are not able to provide that reinforcement which is required for the beam, then you have no choice but to increase the size of your column so that the size of the joint increases. In addition to that, the joint has to be checked for shear strength. And today in IS 13920, you have these requirements given for different types of joints, considering the effect of confinement that these beams and other things will bring in. Okay, so please go through this. This should form an important part of structured design. Remember, in classroom, we often teach how to design a beam, how to design a column. We don't teach how to design a building because we do not integrate all these designs together. Today, there is an occasion where we should be able to teach the integration also, designing the joint at the same time. And those provisions are possible, and we must do those. So in all these, effectively, what you see is that wider columns help. But now this is where you will say, no, larger size columns, loss of plan, the carpet area, and so on. So what do we do? Let's see what we do from a different perspective. So multi-story buildings in India is going to, we are going to build many more of these buildings, not only on the plains, but also on hilly regions. This is, you can see the way this is increasing. So if you pick IS 1893 and go to clause 7 of IS 1893 part 1 2016, you will see this particular clause. And it talks about different irregularities. Irregularities are natural vices based on the functionality requirement that we often bring into the system. It says all efforts shall be made to eliminate irregularities by modifying the architectural planning and structural configuration. So as a structural engineer, it is also our responsibility to talk to our architects who have come up with a basic plan and then discuss ways to improve that further. Okay, don't just say that architect has given, so therefore my hands are tied, I just have to give a design or a drawing. That's not enough. What are these irregularities? Basically, there are 12 irregularities that you will find in IS 1893 part 1. There are 5 of them are related to what is called plan or horizontal irregularities, and 7 are vertical irregularities. You can go through all of them. These are the 5 types of plan irregularities, and these are the 7 types of vertical irregularities, out of which I am going to talk about only 2, the most important ones, which is related to stiffness and strength, because these are related to what is called the soft story and weak story irregularities in multi-story buildings. What is this? We all know the story of Kalidasa. He sat on a branch and cut the support, the root of the whole branch. What happened? He weakened the whole branch and he fell. If you see, we are doing exactly that. This is how I see what we are doing. If you are able to focus, you will see that we are building this huge, stocky structures on these toothpicks, so to speak. What are these? These are the simple columns that we are building, on which we are building these huge, gigantic structures. And why are we doing this? This is for the purpose of parking. You have seen, all these pictures over the years, that what happened to all this. So this is not a 4-story building. There used to be a ground story also with all the cars and everything, precious assets, so-called, all gone. So how do we today kind of do something so that we don't get situations like that again? One of the first things is that we should be able to estimate stiffness and story stiffness. And there are several ways of finding a story stiffness. Simple thing is apply a lateral distribution, V force, and calculate the displacement, the interstory drift, and you will be able to identify. The other is the fundamental lateral mode. Simple thing is, in most of these multi-story building design, we create a mathematical, a numerical model using a commercial software, and usually we do the modal analysis. Okay, and when you do the modal analysis, just look at the mode shape. You don't have to do anything else. Just look at the fundamental translational mode shape. In this example, you see that I'm showing 10 buildings, and In this, there are first 5, and in this, there are the next 5. Out of all these mode shapes, if you normalize them, I see that there is something different in building 5 and there is something different in building 7. You don't have to do anything. You have modeled the structure, you have done the model analysis, just look at the mode shape. You should be able to see that this is something very, very unusual, that everything is happening here and thereafter it's a straight line. What are these buildings? Building 5, building 7. Let's go back. Building 5. No wonder, it's an open ground story building with all the infills in the upper stories. Building 7, same thing. It's an open ground story building with infill walls in all the upper stories. Does this give you confidence? Answer is no, that you know that everything, all the actions are going to happen only in single story. The rest of the blocks are going to just be there. And so, no, it is in all likelihood, these structures are going to collapse in the open story. Right? What are these? These are the same infills are there in all these buildings, but with reinforced concrete structural walls. What happens in those cases? They look pretty simple, decent, and you can see the other aspect that these lower stories, this is more of a shear type behavior, whereas this is more of a flexure type behavior. And we'll come back to this in a moment. So the point is that if we take a building like this and we apply this lateral load, this is the distribution of lateral load. We know that as we come down, the story shear is only going to increase, and therefore, logically speaking, the capacity should also increase. I'm talking about strength capacity, shear strength capacity of the story. But unfortunately, by keeping the story open for parking, which is a practical need, what we end up doing is that we provide a very, very little stiffness and strength to these stories. Why does this happen? Because in the upper stories, we forget that these infill walls are there, and we had a habit of saying that infill walls are non-structural elements. They are not non-structural elements as far as lateral load resistance is concerned. For gravity load, yes, we treat them as non-structural elements, but for earthquake shaking, infill walls are structural elements who provide adequate stiffness and strength. And not only that, they alter the load path, the load pattern also. So therefore, today, IS 1893 requires us to model the infills also as equivalent structs and actually see their effect. So we need to do 2 models for analysis for the purpose of design. One with the infill model, the other one is the bare frame, which we have been classically doing. Not just that, Indian Standard 1893 today mandatorily requires reinforced concrete buildings to be provided with reinforced concrete walls. Why is that? Remember, this is the situation that we in the open story, we have 1/10 the stiffness that is required and about half the strength that is required. Of course, these numbers are not fixed because they depend on the type of masonry, the strength of the bricks, strength of the mortar, and so many other aspects. Okay, these are just representative numbers to give the idea of what is happening. Now, so in all these, we have this kind of a deficiency. To make up this, if we just provide a RC wall, because the RC walls provide so much more stiffness. Okay, let's say it adds 100 stiffness relative to 1 and 10. The ratio now becomes 101 is to 110. Yes, still the open story has less stiffness compared to the stiffness above, but the ratio is not disproportionately, large. Similarly, same thing happens with regard to strength. So yes, with regard, by providing a reinforced concrete wall, what we do is we bring this gap down to a reasonable level. Also, by providing walls, this is the same example that if we have a moment frame and we keep on increasing the size of the column, because remember we saw that smaller columns are trouble, so we need to increase the size of the column. Remember, earthquake is a displacement loading. So the more stiffer we make the columns, the more force they are going to draw. But instead, if we provide walls nicely, what we see is that the total moment in the interior columns come down drastically the moment we start providing walls. So by providing RC walls, you will actually make your column design more economical than not providing the RC walls. So this is where the clause is that particularly open ground story building shall be provided with walls in select base. You don't have to provide it everywhere. Okay, and how much of wall? The current requirement is at least 2% in each principal plan direction, in each direction. How to design these walls? That is where IS 1390 comes in, and there are provisions given for walls. Now, what is a wall and what is a column? This is a very important thing that we need to understand, that we deliberately elongated our columns beyond the aspect ratio of 2.5 because suddenly the vertical reinforcement requirement comes down from 0.8% to 0.25%. So instead of keeping a member, vertical member, with aspect ratio less than 2.5, if we just make it 2.6, we can call it a wall and therefore reduce the vertical reinforcement. This is a bad practice. This is a bad practice. And so now you will see that a gradual transition is given in IS 13920. This is also important because it is consistent with the behavior of the wall. Because squat walls will behave in a shear manner, whereas tall walls will deform in flexure. So the behavior itself is different in these two situations, and therefore the nature of cracking and the requirement of reinforcements are going to be different. So there is a detailed table now given in IS 13920 where you will find the requirements. Of course, there are some typographical error which are corrected in the amendments, so please look into the amendments. Also, it is beneficial to provide the boundary elements, but only thing is analyze the entire cross section as a whole and not in parts, that you analyze the boundary elements separately and the wall separately, the web of the wall separately. Of course, for preliminary design, we use some thumb rules, that's all fine, but final detailed calculation has to consider should consider the entire cross section in totality, right? Yes, it's not a crime to provide openings in walls, but the only case that we need to care about is what is the relative size of the openings within the wall, because depending on the size of the opening, the entire load transfer mechanism changes in the walls. So if you have a very small one, it is predominantly a shear dominated behavior. But if you have large openings, you will see that these become essentially two columns coupled in between. And so this design of the coupling beam also becomes important. Otherwise, these two portions of the walls will start acting independently. Okay, so there are design provisions given for these. Detailing is given in IS 13920. Only thing I want to highlight is that no matter what, remember IS 456 table 20 is about tau C max. Under no circumstances that tau C max should be violated. Okay, so this is a very important thing that one must remember at the time of design. So I'll close by saying, by drawing your attention to one important thing. So what I tried to do was to emphasize that seismic design is not a costly affair, because we have already optimized, we have already reduced the force to 1/10 right at the beginning, saying that we'll allow damage. But still, many of you will not be convinced. Some of your clients will not be convinced and will say, no. Sir, whatever all these requirements that are given in the design codes actually increase the reinforcement requirement. My first answer to you is that you are comparing apples with oranges. You are comparing the reinforcement requirement between a structure which is designed to resist earthquake versus a structure which is not designed to resist earthquake. In other words, you are comparing reinforcement requirement for an earthquake resistant structure which is safe versus an unsafe structure. Please don't do that. Even if you're not convinced, we will highlight one more aspect to you. Let's say this is the plan of a building which we have to design, and those are the columns that you see, and the dotted lines represent the central line of beams. Nice rectangular ideal structure. Of course, no structure is ideal like this, but let's assume this. In this, if I ask what is the lateral load resisting system, and essentially asking which of the beams, which of the columns where we have to follow all these requirements. The most times, at least few years back, till few years back, the answer used to be all the beams, all the columns. The answer is no. All we have to do is identify a set of frames that will design as the lateral load resisting system and apply all these requirements only for these. If you read the foreword of IS 13920-2016, it states this very, very clearly. All RC frames, RC walls, and their elements in a structure need not be designed to resist lateral loads, and therefore follow all the requirements of strong column, weak beam, detailing, size of column, joint design, and so on and so forth. Therefore, how do we identify this? Right? Here I want to bring to your attention a very important aspect. Let's take this example of that same example building. We have 3 bays on this direction, 5 bays on this, 4 bays in this direction. Let's consider these vertical frames. So we have 1, 2, 3, 4, 5 in vertical frames in the vertical direction in the y-axis, let's say, and we want to consider only these 2 frames as the lateral load resisting elements. And to begin with, I have the beams as 400 by 300 and columns as 400 by 400 everywhere. If I analyze this and I have a rigid diaphragm also, plan aspect ratio is nice. So I'll consider rigid diaphragm action for monolithic construction. The question is, when I apply the lateral load, earthquake force, design force in the y direction, how much force will these 2 frames carry? Simple answer is, since everything is same, each of these 5 frames are equal, these 2 together will only carry 40% of the load. So we cannot declare only these to be the lateral load resisting frames and not design the remaining 3 for all these requirements. We have to ensure that these 2 actually draw a larger part of the lateral load. How do we do that? Because it is a displacement loading scenario, these frames, if we make them stockier, if we increase their stiffness, then automatically they will draw more force. So there are various ways of increasing the stiffness of these 2 frames. What I've done here as an example is only increase the column size. Of course, these are very big numbers. Don't get perturbed by these. If this looks very bad, we'll provide wall, let's say in 1 way. But the point is, you need to make these systems stiff so that automatically the percentage, the share of load that they draw upon themselves increases. So let's say you can draw a line, let's say at 90%, 95%, then you can say that, okay, only these are my lateral load resisting systems. Therefore, for these frames, I'll follow all the requirements. For the rest, I will do simple regular design as per the requirements of IS 456. Similarly, in steel buildings, the same case you can do. Another possibility in steel buildings is, instead of providing moment connections, you can provide simple connections. That helps a little bit. But what I'm trying to draw your attention to is the fact that it is not enough to declare certain frames to be lateral load resisting elements or manipulate by releasing moments in your numerical model. That is not the way to identify or declare a certain frame as lateral load resisting frame. You have to make it happen, and that will happen only when you actually proportion the stiffness also and the strength. Talking about stiffness, the easiest way we saw is to provide walls in select bays. But the one important thing that now we are stating explicitly is that these walls cannot be a floating wall. Okay, this was the picture in the earlier version of IS 1893, which kind of gave a wrong impression that so long you provide these walls here, it is perfectly fine. But no, current 139200 clearly tells you that no, these walls cannot be founded on beams or any transfer girders. They have to be taken logically to their foundations. Otherwise, what will happen? You will see these kind of column failures. You can't try to support an elephant on ants. Few other important items: flat slab construction. earthquake after earthquake across the world, you will see that collapse of buildings primarily has been attributed to flat slab. However, in India, we are left, right, and center building flat slab construction. So, for the first time, you will see that IS 1893 acknowledges flat slab construction as a system. But until further research is done or further, things are kind of agreed upon, there is a penalty that is provided. So in regular case, you will see that the drift under the design load is permitted to be up to 0.4%. Here, the drift is limited to 0.1%. Essentially, what does it mean? It means that you have to provide stiffness. Strength is not the sole criteria. Trust me, when I said right at the beginning, I do not care much about strength. It is stiffness and deformability that will, decide whether your structure is going to collapse or going to continue to stand. Okay, so these are the special statements that are now there in IS 1893. Precast systems untested even today, and therefore I saw many people saying that I have detailed the beams, I have detailed the columns as per the requirements of IS 13920. Is my precast structure safe? The first point is the energy dissipation capacity that is envisaged by IS 13920 is through ductile flexural actions. In precast, all the actions happen in the failure happens in the connections, and they are not tested. We first need to develop standards for testing, test protocols, do testing, and then come up with separate, guidelines for them. IS 13920 is not applicable for these kind of construction. So please do not use them. Do not encourage others to use them for that purpose. Finally, what did I try to convey through all this exercise? Please focus on behavior. Code provisions are to be followed in letter and spirit. Yes, that is part and parcel of our teaching job, that we must teach our students to do that. And as practicing engineers, it is your responsibility to do that. But don't lose sight from the focus. Typically, we have to build a structure. We analyze a bare frame. We design a bare frame. We think that this is how it is going to behave. But the moment we provide these infill walls, the behavior changes drastically. We should be able to understand this. So this is why this is what I call as ABCD of earthquake resistant design, is that please analyze. Your whole analysis should have a purpose, and that purpose is to reflect the behavior of what you are going to construct. Your behavior, because your behavior is going to depend on what you construct and not what you analyzed or what you designed. What you are going to finally put on the ground is what is going to dictate this behavior. So therefore, at the analysis and design stage, whatever you have analyzed and designed, please construct only that. Don't add things later. And the purpose of design is not just to make a structure pass your scrutiny or economical, but actually to control the behavior. So the whole idea of design has always been to control behavior, particularly more so in earthquake resistant design. Okay, so this is what you will find in the book, Some Concepts in Earthquake Behavior of Building. Design is always to control behavior. Analysis is to reflect that behavior, and the focus is always on behavior. I'll stop here for today. So what I will say is that yes, there are many things in various standards. We need to start to understand and implement all these. There are shortcomings. We need improvement. That is why even worldwide, people, different countries, they keep on updating, revising their standards. We take too long in our country, but hopefully, in years ahead, we will do a better job at that, so that we'll all improve these clauses. But that will happen only when more and more of us participate in this activity. So this is my, hope that in years ahead, we'll have more participation from many of you, particularly faculty members, teachers in engineering colleges. Just to facilitate all these things, I have been fortunate enough to be part of some of these activities through GSDMA and LDMA. If you find some time, I'll be happy if you can go through these documents. Do share your feedback on this. I'll stop here, not before saying that I'm grateful to Professor Sangvi in particular. It's been after a long gap that suddenly I got this call from him. So I'm grateful for this opportunity, and of course we all will always be grateful to our teachers, students, and colleagues also, from whom we keep on learning every other day. Of course, I have taken some photos and images from the internet, for which I'm also grateful. I'll stop here. Thank you. Jai Hind.
Thank you so much, sir, for such an intellectual and informative session. This would have surely benefited. Thank you so much, sir, for such an intellectual and informative session. This would have surely benefited all the participants in enhancing their knowledge on the concept of earthquake performance of concrete buildings and core provisions. You made various concepts and fundamentals crystal clear by using various practical examples. Many peculiar topics you touched today, like structural behavior, damage and failure, various virtues of earthquake resistant structures, crack section property, modes of failure, location of damage, capacity design of RC beam and columns, seismic design codes, stiffness irregularity, RC structural walls, etc. really helped us a lot to learn. Thank you so much, sir. Now we are open for question and answers. So anyone, if have any questions, can raise their hand.
I think Mr. Bhupendra Kumar Panchal has his hand raised. You can unmute. I believe they can unmute and ask the question. I'll be even happy to see if you can turn on your video. That would be wonderful.
Am I audible, sir?
Absolutely.
So it was a wonderful session, sir, and all the principles which has been covered. Usually, if we say reach to the doctor, he will prescribe so many medicines. But unless doctor tells why these medicines are there, so patient will not be cautious. So similar things happens without understanding the principle. If one starts designing, so lot of question comes. So customer would not like to have all those medicines, but our structural engineer has to convey why it is required. This is what is our role. You have taught these all principles, sir. My question is regarding the infill effect, sir. In the code, it is given that when height to thickness ratio, aspect ratio of the wall is less than 12,
yes,
then we can have the same thickness you can adopt. But if it is more than 12, code is silent.
Yes.
So we need to neglect that, or we have to calculate it, sir?
Yes. So there are two parts to answer is both yes and no. The expectation is that if you have a very slender wall, yes, during earthquake shaking, particularly in the outer plane direction, those walls are going to fall, collapse very early in the shaking. Yes, so once they fall, then they are not going to participate in the stiffness and strength, thing in the perpendicular direction. So that is the thing. Now, is that a good thing or a bad thing? That is where we need to go to ISO 4326 and say that we need to have a wall not exceeding a certain slenderness. So that's another part of the whole discussion, right? At the same time, I agree with the intent of your question that even if it is, let's say, 13, 14, those walls may not fall and therefore contribute stiffness and strength, which by remaining silent, we are giving as if a hint that you need not consider. That can be little unrealistic. So yes, maybe in a future revision, we need to talk about it a little more explicitly. See, what happens is sometimes when you are not sure, you stay silent.
Right.
Something similar happens all the time. Very important observation. Yes, I agree with you on that.
Got it, sir. Thank you, sir.
Any other question? Yes.
Good afternoon, sir. This is Lokesh.
Good afternoon.
I have a couple of questions, sir. One thing is, in the initial stages of the slides, you had shown one complete steel structure which had collapsed. You also mentioned that complete steel doesn't mean a guarantee against earthquake. So what could be the probable errors that could lead to a failure of such a complete steel structure, or any specific do's and don'ts when you do full steel structures?
Okay. Remember, I had two slides, one for reinforced concrete structures and another for steel structures, where I was discussing about the different modes of damage, ductile and brittle. In steel, you will see that buckling is a major issue. Okay, and buckling can be of three types, essentially: local buckling, distortion buckling, and global buckling. And global also is member phenomenon and at the structure level also. So there are two levels to that. When we design structures with steel structures with hot roll sections, which are pretty stocky, the thickness is more, we don't have distortion. In that building in Mexico City, they used box columns with relatively thinner steel plates as the sides of the box without stiffness, and there was local buckling, thereby opening of the weld, and which triggered the global failure. This was one of the aspects. In addition, there was inadequate beam to column connection also. So there are multiple things which together trigger a collapse like this. So buckling is a very bad, very important aspect that needs to be taken care of in design of steel structures. Right? And connection failure is the second most important, rather the most important thing in steel structure design. If these two are not taken care of properly, although steel is a very ductile material, steel structures can be extremely brittle.
Okay, sir. I have one more question, sir. This might be a little deviating from the main subject, but
Go ahead.
I'm just curious to know. I've always wondered why, certain heritage buildings which you have, like our forts or palaces, they are kind of very durable and they last for a long time, even in spite of a lot of calamities. Is there any particular thing which we can learn from that, which we can apply in today's structure, sir? Is it just the quality of construction or the quality of material or the span, or what could be the probable secret they have which we could learn?
Okay. I believe I saw that you have another talk on heritage structures or masonry structures somewhere.
Okay.
Maybe a lot of discussion will happen there. But even without getting to heritage structures, even reinforced concrete structures or steel structures, which were built 50 years, 60 years back, we find many of them are still in good condition and working. One of the reasons for material deterioration is the stress level. Earlier, and this might not seem very obvious right away without going through a detailed discussion, but nonetheless, I'll say this. Earlier, we used to keep the stress level at a much lower level relative to the strength, the yield or whatever.
Okay.
But today, in the name of making more optimal design or optimization and so on, so for more economic designs, in simpler words, we are trying to reach very close to the strength limit of the material. Now, this is one of the reasons why we see that faster material deterioration is happening today, and it is also eventually affecting fatigue life of structures and a lot of other things happening. So fundamentally, if I have to just, without getting into the details of anything else, just point out one aspect which probably leads to higher life of older structures relative to what we are constructing today. It is because they used to keep the stress levels much lower than what we are doing today.
Okay.
Which has a large number of implications going forward.
Thanks a lot, sir.
Thank you. Yeah. Any other question? Okay. If not,
Thank
then
you,
we
sir,
can continue.
for answering all the questions and providing us your precious time. Sir, it would be great if you can share your PPT with us.
Okay. Let's see. You're
Sir,
you're
our
recorded. Okay. Fine.
Sir, our email ID is head_applied@ldc.ac.in. So
Okay.
please take a note. I will repeat.
No, fine. I'll get in touch with Professor Ambi.
Okay, sir. Okay, sir. Thank you so much, sir.
Thank you so much. Thank you, everyone. Have a good day. Bye.
Now there will be a break till 2:30 and next session will be conducted by Dr. S.D. Bharti on use of earthquake energy dissipation devices in buildings at sharp 2:30. So be ready for the next session. Thank you so much.
Thank you.
Now you can leave the meeting.